This is Module 17 of Mechanics of Materials Part 2, and today's outcome is to solve an actual column buckling problem. As a review, we looked at critical buckling loads for different end conditions. This was for pin-pinned, this was for pin-fixed, and then we had fixed-fixed and fixed-free. We called the denominator the effective length squared, and it's defined there, and then we saw physically the length of, or the effective lengths as shown with the graphics. And now let's do a worksheet. We've got a truss below composed of 1/2-inch diameter structural steel bars. The normal yield stress for the steel is 36 KSI. The modulus of elasticity for the steel is 29,000 KSI. We're going to require a factor of safety of 3 with respect to yielding due to the axial load. And we want to find first the allowable load due to axial loading, and then to find the allowable load due to buckling, and then see which case will govern. And since this is considered, we're going to consider this a perfect truss, we're going to say that we have end-to-end conditions for our members. And so we want to start by solving the axial loads in the truss member. This goes all the way back to my second course, Applications in Engineering Mechanics. If you need to go back and review that, I recommend that you do, but this should be a quite straightforward problem with the techniques that we learned in that course. So how should we begin? Well, we're going to do a free body diagram of the entire structure. Do that on your own. Come on back. We see we have pinned roller connections, and so these are the force reactions that we get as a result. And then what? Well, we're going to go ahead and sum moments about point A here, and that'll give us the equation for solving for By. We find By. Then I can continue on, solve for the forces in the y direction, set them equal to 0, and I'll solve for Ay. And now let's go ahead and do a joint cut. And the joint cut will allow us now to find the actual forces in members AD and AE. And all of these forces in all of these members will be in terms of the force F that we're trying to support. And so go ahead and do this on your own. Find FAD and FEA or AE, and then come on back and let's see how you did. And so there's the free body diagram. If we sum forces in the y direction, we can solve for FAD. And this is the result we get. You can see by symmetry now, since this is symmetric about the center of this truss, if we put a mirror in the center, the left-hand side looks the same as the right-hand side. And so since we've solved for FAD, that also is the same as FCB, or BC. And so we've taken care of 2 of the members. Let's continue on. Some forces in the x direction. And when we do that, we know what AD is now. We can substitute that in. We get FAE, and that's our FAE is this member. And so by symmetry, it's the same as FBE. And so now we've taken care of this member, this member, this member, and this member. So we still need these internal 3 members. How would we go about solving for those? Well, we could continue the joint method, or we can do a section cut. And so let's go ahead and do a section cut. Draw a free body diagram of that section. We'll sum moments about E, and we get this equation, so we can solve for FCD, which is up here. We then go ahead and sum forces in the y direction. We can solve on our section cut here for FDE. If we know FDE by symmetry, it's the same as FCE. And so now we have solved for the internal forces for all of the structural members of our truss in terms of this load F. Now, to find the part A, the allowable load F due to axial loading, we're going to use the maximum shear stress theory, which says that failure will occur when the shear stress in any of the members is greater than the failure shear stress. And this theory is used because it's good for ductile materials, as we've seen in my past courses and lessons. And so ductile material being a steel in this case. For an axial load then, the failure shear stress will be equal to the the failure normal stress or yield stress divided by 2, or in this case, the yield stress for the normal yield stress for steel is equal to 36 KSI, so the shear failure stress is 18 KSI. And this is based on a simple tension test. As we've talked about before, if we used more circle and we were doing a simple tension test on any of these members, we would see that sigma failure is 2 times the tau failure. Okay, so we have our axial load failure for shear, and we have to now include the factor of safety, which we want to be 3 for yielding. And so therefore we have our failure stress, which is 18 over whatever our actual stress is going to be, which says, okay, our actual or allowed stress can only be 6 KSI or less. And so here again, the simple tension test for Moore circle, I've shown now the actual or allowed shear stress. We see the actual or allowed normal stress. We know that they're related by a factor of 1/2. Here's our truss. And so for our loads in our members, since these are axial loads, the normal stress is equal to the force in those members divided by the area. I know what the cross-sectional area is because I'm given that in the problem statement. I know what the forces are because I've solved for them. These equate to the P's in any given situation. And so P allowed then, the worst case will be when in member CD, where we have a compressive force of 0.75 F. All the rest of them are going to be a little bit less than, or going to be less than 0.75 F. And so this is the critical condition. We take the 6 KSI, we multiply by 2, we multiply by the cross-sectional area, and that we find then the actual or allowed F that we can support in our truss has to be less than or equal to 3,142 pounds or 3.142 kips to avoid yielding. And so we've done part A. We found what we can hold as far as yielding is concerned in our truss members. Now let's go ahead and look at the allowable load due to buckling. And these are all pin-pin conditions. Again, the situation with the worst or the largest load will be in CD. For member CD, it'll be in compression, so it can buckle. And so we put in our values for our critical load, and we find out that the critical load can only be 0.1694 kips, but that's equal to 0.75 F critical, the F critical that the truss can hold. And so we see that the critical force that can be held in as a result of member CD is going to be 226 pounds. And so the actual allowed stress for yielding was 3.142 kips, and so the lesser of those are obviously the buckling condition. And so if we get to a load, a force that's greater than this, we are going to go ahead and have buckling in member CD. And so that's the limiting condition. And so that's the case that governs. We've solved our problem, and we'll come back and continue on.